From Pads Layout, we will launch FloTHERM XT from the Tools, Analysis, FloTHERM XT menu pick. The first thing that happens is that we will be asked to create a new project using the wizard from FloTHERM XT. The first requirement is to create a directory and a project name. You can use the Browse button to find a preferred location. Notice that as I type the project name, a subdirectory is added in the location selected into which all the files will be saved, the geometry files and the result files. Then we have the environment types. There are 5 environments available. For this demo, we will be using the internal enclosure, which will create a completely sealed box with assumed conditions outside. Analysis of the objects placed inside this box, including the imported board, will take place, and there is no air transfer between the inside of the box to the outside defined. This window allows you to customize units. We'll scroll down to length and change it to millimeters. Then to velocity and change it to feet per minute. We also have predefined unit systems, international and US, that can be used as well. This window allows us to define the internal enclosure, which is a sealed box. Under enclosure dimensions, we fill in the dimensions of the box. Under gravity, we can change the gravity direction, but we will use the default negative Y direction. Under global ambient, we define what the outside temperature is. 35 degrees Celsius is a value that is quite often used as worst-case scenario conditions for electronic cooling design. Let's say if the device was going to be in desert conditions. But you can change it to a temperature of your choice. Then we have the heat transfer coefficient, which is how any heat that gets into the box gets out into the ambient. This is set to the default of 5 watts per square meter Kelvin, which is a good representative number. By default, the simulation will take into account both conduction through solid materials and also convection in the air. A third method of heat transfer is radiation, which is the surface-to-surface transfer of heat. Under radiation, we'll click thermal radiation, and as you can see, you can set the external radiant temperature, radiation surface emissivity, and solar reflectivity. For simplicity, we'll keep radiation off. This window allows you to select the default material for the project. This material will be applied to all solid objects unless we specify otherwise. It's very useful, for example, if you have 100 parts that are plastic and only 1 aluminum. Then you would set this to plastic. It saves you time setting up, and it allows the solver to actually have something to work on. In this example, we want a plastic enclosure rather than the default aluminum alloy. FloTHERM XT is supplied with a large range of materials in the library. We will expand out the library and go to Attributes, Materials, Polymers, and select 9166. This window gives a summary of everything we have selected so far in the wizard. If we scroll down, you will see the dimensions of the enclosure, domain type, solution, and analysis type, which were populated when I selected the internal enclosure environment. When you click on Finish, you will see in the background it will start to create the project. The first thing it will do is create the enclosure as set in the wizard. The user is now prompted to continue with the addition of the board. We'll click OK to continue. Because we are coming from pads, it knows we've got to import a CCE file. So it's confirming this with this dialog box here. it will ask for a component outline, whether it's placement or assembly. If this is unknown, then use the default assembly. When components are placed in the layout tool, the component height is not always set, so we have a default component height setting. The board we are using here is fully routed, so the copper traces can be read from the CCE file. However, if the routing has not been performed, or you simply want to ignore this, we can toggle on the Use Assume percent cover to set the percentage of copper in signal and power planes. Note that we can also define the copper in the dielectric layers to represent vias and interconnects. Since the board is fully routed, we will uncheck Use Assume percent cover. We can now see FloEDA bridge appear. We have our board outline and layer definitions. For each layer, it has worked out the percentage coverage of copper and shows you visually as well. If we click on VDD Mix Plane Layer 4, you will see it has approximately 90% copper. Note the thickness of the layer as well. If we click on a dielectric layer, it can be seen it takes into account all of the vias going through it, so we still have some percentage of copper in the dielectric layer as well. We'll expand the components section. Here we have a list of components, a number of which are grayed out. If I select one of these, you can see that they are filtered. When we are looking at a thermal analysis of the board, we are only interested in thermally significant components. Now, these will be ones which are large, usually have a high power output, and important in terms of the junction temperature being something that we are interested in. We may have a number of very small components which won't create blockage to airflow and don't have high power densities, so we can essentially ignore them in the calculation. To work with this, we have a filter button. We can actually filter depending on footprint dimension, height, power, and power densities. We also have a holes filter as well, so if you have large holes in the board, these might be significant because they allow air to flow. We will set the footprint dimension to less than 6 millimeters and set the hole size to less than 3 millimeters. We can't make any changes to the layout because by default, when transferring to FloEDA Bridge, we lock the layout. By unlocking the layout, we can make changes to the board within FloEDA Bridge so we can update and move components. If we click on the lock icon, this will unlock the layout. Now, we'll select one of the components by clicking on the board or the componentry. As you can see, we get the information regarding its location, whether it's on top or bottom of the board, the size of it, etc. If some of these came in from PAD's layout with no height defined and have the default height, we can now change them in FloEDA Bridge. From a thermals perspective, we have a number of ways in which we can represent a component. The first level of model is simple and represents a component as a block. You can also see we have material as typical plastic package. If you click on the material dropdown, you will see that we have a number of material properties to pick from. You can select the material appropriate for the type of component, and it will give you a fair degree of accuracy, particularly in terms of temperatures that will be achieved. The next level of model type is tube resistor. The tube resistor model populates the resistance from the junction to the board and resistance junction to case. These will give you reasonable accuracy on junction temperatures for that particular component. In FloEDA Bridge, you can add models to components from the component library. We will select the component in the middle of the board, click on the component library icon, and navigate to the components folder. We will select this 2 resistor model and click on Swap for Selected Only. Observe the change in the thermal details, which will be the library to resistor instead of simple. We will repeat for the other large component. Again, notice that it has updated the model type under the thermal details dialog. The components have now been swapped with a library to resistor. Notice that it has filled in the junction to board and junction to case thermal resistances for you. Quite often, it will be a manufacturer-supplied model. There are higher levels of modeling, or the die, package, and pins are modeled. As you go up the modeling level, you get more accuracy, but the trade-off is that it takes longer to calculate the simulation. From a FloTHERM XT user's point of view, the modeling decision is typically based on what data is available, rather than design intent. In an ideal world, we would always want people to use the best possible modeling data that is available. For this simulation, we will be using simple models for the ICs, and we will change the large ICs back to simple models. We can also use different modeling assumptions for the board itself. We have compact or detailed. The compact model that we have just creates a single block to represent the board. You do not get such good heat transfer into the board and then spreading into individual layers. With the detailed option, the board is represented as a block of FR4 with small amounts of copper to represent interconnects in each copper layer separately, with the appropriate thermal conductivity based on the percentage of copper in that layer. This means that we can have the heat spread more accurately as it travels through all the layers. For this simulation, we'll leave the model as compact. All these different modeling levels are there to allow exploration of simple models early in the design process, all the way through design closure with more advanced models. Now, the next thing is power. We have the ability to import power lists, which is simply a file with a reference designator and the associated power next to it. Alternatively, we can select individual components and update the power manually. We'll click on Import Power List to import the power list. Notice that under Thermal Details, power has been populated. The power list contains power for components that in this case have been filtered, so will not be modeled explicitly. However, this power will still be applied over the surface of the board so that the total power in the system will be correct. We will now transfer to FloTHERM XT by pressing the Transfer to FloTHERM XT button. In the Model Summary window, you can see the total power dissipation. If this is actually 0 and you don't have any power on the board, it will pause at this point to say, we've got 0 power. Are you sure you want to transfer? It also shows the number of unfiltered and filtered components. The software goes through and creates the geometries of all of these parts. If it's a complex board, it takes some time since it is creating CAD models of each one of these individual items, and then associating, for example, a 2 resistor model onto it, adding thermal attributes to the components, and associating with any thermal radiation if it were selected. Both the enclosure and board are located at 000. Now you'll notice in the internal enclosure, you have a little F next to it. This means it's fixed. I cannot move that object unless I cause that to be floating. The board, however, is free to move, and you can set it within the enclosure visually. Not always the most accurate way of doing it, though. With the CAD functionality, we have a concept called mates. We'll rotate the model and click on the back of the board. Then we'll select the paperclip mate icon. And this will give us access to the mate's property sheet. Now, we will point and click the mouse over the back of the enclosure and observe the outer surfaces highlighted. The back of the board is now fixed to the back surface of the enclosure because the default for mates is coincident. Note the two surfaces that were selected under mate selections above. If I click on the measure button, I can then define an offset, let's say 13 millimeters. The board is now 13 millimeters from the back surface of the enclosure and will not move more than 13 millimeters off of that surface. We'll click the checkbox to save the mates. We have the ability to go back and change the thermal representation of a component or change whether you are modeling it as a detailed or compact board. In the components tree, click on the board and then hover over this green button. You will see that it says Edit EDA Data. Clicking on it reopens FloEDA Bridge on this board. You can also update components within FloTHERM XT. Here, you can make changes to the modeling level of the board, compact or detailed. If you click on Layer Definition, a dialog box will appear where you can update layer thickness, percent cover, conductor, and dielectric material. We will select one of the components. Under Attachments, you will be able to access the FloTHERM XT parts library and update the component material. You will also be able to set the convergence control and monitoring goals, which I'll talk more about when we simulate. So it might be that we need to add in more geometry. This can be by importing or creating CAD geometry, using library items, or as we will do now, using FloTHERM XT Smart Part Library. If we click on the Smart Part Library icon, you can see the Smart Part Library includes geometries such as simple cuboid, cylinder, enclosure, fan, and multiple types of heat sinks. It also includes non-geometric parts such as fixed flow, heat pipe, and pressure. We are going to add a heatsink. We will double-click on Heatsink Circ Inline. You can confirm the name in the component tree. Observe the default heatsink and double-click on the heatsink in the tree to access its property page. This will allow us to set up our heatsink. First note, under Attachments, that the material is defined as nylon 66. The brackets denote that this has been inherited from a wizard setting. Using the drop-down, we can change this to any other material in the project. Clicking the button next to the drop-down opens the FloTHERM XT Parts Library. Now we will navigate to the alloys and select aluminum 5052 as the material for the heatsink. Under Base Geometry, we will set the dimensions and the thickness of the heatsink. Under Pin Geometry Information, we will set the number of pins, diameter, and length. Observe the changes to the heatsink. Now we will mate the heatsink to the IC. First, we will select the top surface of the component approximately in the middle of the board and enter the Mates property sheet by clicking on the paper clip icon. Next, we will select the underside of the heatsink. We will expand Advanced Mates and select Profile Center. This matches the centers of the two faces referenced under the mate selections. Once everything is set up, we'll want to start looking at our simulation. To run the simulation, click Solver, Solve. On the bottom left in FloTHERM XT, click on Thermal Analysis. The Goals dialog will open. Convergence goals are values chosen by the user to follow the behavior of the components and help the simulation converge to a steady-state solution. Goals are automatically created when the board is transferred from FloEDA Bridge. We will open a component and look at its properties. You can see under Convergence Control Goals that the default is maximum temperature. It might be that the average temperature in a part is critical in our convergence, so you can have it converge to the average temperature as well. You could also converge to maximum temperature and monitor the average temperature by activating it under Monitoring Goals. If we scroll down and pick a component in the Thermal Analysis pane, it highlights on the selected goal window on the right-hand side. The selected goal starts to slowly converge, and after about 10 iterations, you really start seeing it ramping up. As it converges, the plot starts getting flatter and flatter as it goes to a converged solution. In the Normalized Goals window, we can see the plots for all of the goals. You can select a number of goals by Control-click and see them populate in the Selected Goals window. You can zoom in by left-click and drag to get a closer look at the temperature the selected components are converging to. Right-click, Reset Zoom to reset the view. You can hide the graphs by pressing on these arrows here. We can filter as well, by parameter or by calculation, for example. This last column shows a check on all the components whose set criteria has converged. Now we will interrogate the model. Here we are looking at the surface plot, and as you can see, the temperature is almost 182 degrees Celsius, well above the upper limit for junction temperature of semiconductor devices, usually on the order of 150 degrees Celsius. I will now hide the surface plot, and under plane plots, double-click on the Z plane plot. Under General, click on Show to show the plane plot. We will unselect Mesh and click on Show Manipulator to activate it. Using the manipulator, you can drag the plane through the model. Under Scalar, we can change the data of the plot. We can look at temperature or airspeed. We can also show annotations for plot maximum or minimum. The annotation appears showing where the plot maximum is. Now we will unselect the scalar plot and show the vector plot. Here you can see the direction and speed of the airflow in the enclosure. Notice the airspeed is upwards of 25 feet per minute in this section. As seen on the plane and surface plots, there are some high temperatures on the board, the highest reaching approximately 182 degrees Celsius. There are a number of reasons for this. The models we are using for the ICs are simple. We will step up one model level and replace the IC's simple models with 2 resistor models. We will also update the board model level from compact to detailed. Also, the board is simply floating, so there is no conduction path to the casing, and there are no vents in the box to allow cooling air to enter. So we will update to a more complex housing. Additionally, we have taken into account conduction and convection, but not radiation. This can be significant in cases without forced cooling, where there are high temperature differences. We will go back into FloEDA Bridge to update the board and IC models. Click on the corporate board, then click on the Edit EDA button. Click Yes on the Replace Board Assembly dialog that pops up. And it takes us into FloEDA Bridge. I will select the board and change the model level to detail. Remember that we have already loaded the 2 resistor models for the ICs. I'll click on the ICs and change the model type to Library 2 Resistor. Now we are ready to transfer back to FloTHERM XT. Under the Models section, I will double-click on Model Data. Under General, I'll click on Thermal Radiation to activate it. We now need 2 entries. Default radiation surface emissivity is a property of the surface involved in the radiation. It is a value between 0 and 1 and defines the amount of radiation, 1 being a black body. Generally, plastics, such as the more complex model of the enclosure, are a high value, so I will use 0.9. The external radiant temperature is the temperature of surfaces outside of the model that can be seen by any radiation process. Generally, a suitable value is the same as the external air temperature, which in this case is 35 degrees Celsius. We have a metal heatsink, and generally, shiny metal has a very low emissivity. I will select the heatsink and then click Remember Selection. Now I'll navigate to the FloTHERM XT parts library and I will double click on Radiation Surfaces. I will enter an emissivity value of 0.05. And click on Restore Selection. This step is necessary as we still need to define which surfaces we require. We are now going to investigate changing the enclosure used to a more realistic case from our library. First, I'll select the enclosure, right-click, and either delete or suppress. Delete will permanently remove the object from the project, whereas suppress is a way of removing it from the project, but it is still readily available if we want to use it again. In the FloTHERM XT parts library, I'll expand the Pads XT workflow library to find the enclosure under mechanical parts. Double-clicking on it will automatically populate the enclosure in the component tree. Now I will hide the top enclosure. Next, I will make the top surface of the mounting hole to the back of the board. I'll then make the outline of the mounting hole in the board to the circle in the mounting pillar. With these two mates, the board will lock to the housing. Now, I'll change the transparency of the top and bottom of the enclosure. Previously, the solution was set up assuming that the outer box was fully sealed and we are only interested in the results inside the box. However, this new enclosure has vents, so we need to solve the flow through the vents both inside and outside the enclosure. We need to make changes to the solution type and set the volume for which we want results. We'll go to Overall Domain and change the domain type from internal only to internal and external. We now see dimensions for the overall size. We'll click on Edit in View, and as you can see, it allows you to drag the sides of the ambient and fit it around the model. Alternatively, you can type in the values, keeping the mode as start and size. The board contains some components that penetrate the bracket. However, the corresponding holes in the bracket have not been modeled in this case. So that we have the correct conduction properties in the intersection, we can reorder the model hierarchy. The simple rule is that the objects defined lower in the tree will overwrite those defined earlier. We'll select the enclosure and press the promote button until it has moved above the board. At this point, we are ready to simulate. Let's right-click on the surface plot and select Show Annotation for Plot Maximum. You can see that the high temperature decreased to 105 degrees Celsius, approximately 74 degrees Celsius less than the last simulation, and well below the upper limit for junction temperature of semiconductor devices, usually on the order of 150 degrees Celsius. This is due to the two resistor models we introduced, as well as the detailed model for the board. Also, connecting the housing to the board will create a conduction path from the components through the board and to the housing. The model will then interact with the ambient temperature through convection. I will now hide the surface plot and select the Z-plane plot. Now, I'll rotate the model so it shows the back of the board and drag the manipulator to where the edges of the support legs meet the back of the enclosure. Note the hot spots occurring around the support legs, showing the heat transfer from the board to the housing. Let's look at the vector plot. Now you can start seeing a very complicated look in airflow. Since hot air rises, the air passing through the heatsink is rising. The airflow created will impact the way in which the heat is transferred off that surface. Notice the air in the enclosure gets up to approximately 22 feet per minute in this area. Generally speaking, if you have faster airflow, it will pull more heat away from the surface, hence the reason the designers will put fans into a system. The default values used in the solver to say that convergence has been achieved are robust. The meshing technology used to create the computational cells is very robust in creating a good mesh. There will be some cases where you might have to refine the mesh because you have a narrow channel that's very critical. But all of that is more advanced. You can get very useful results from default mesh and solver settings. So, with FloTHERM XT for pads, you can quickly set up and perform a thermal simulation early in the design process to help guide design decisions for later stages and ensure the most cost-effective cooling solution is chosen by considering the effect of all aspects of the design, such as package selection, PCB layout, board structure, and enclosure design. This concludes the demonstration.